And this is our a Boolean expression for an AND, right? If all inputs are high, the output will go high. This is the abbreviation version. All highs equal a high. Now, what's different between our expression and what's different between our Boolean equation is on the Boolean equation, the output comes first. And then the input becomes second. Okay, do y'all understand that? So normally when we draw a game, just for this class, and I'll show y'all some actual schematics. It's normally what they do on most digital schematics is they come up here and they give every logic gate signal some type of name. So that's the way we start off with some type of AND signal. And how many inputs can this guy here have? An AND gate. A minimum of 2. Can have a bunch, but it's got to have at least 2, right? You understand? Then we'll come up here and we'll give these things names. This might be something like, light off. This might be something like neutral. And then, not nut. That's good though. And then something else like seat belts. And then this might be, we got one where about what your car looks like to be able to start. So what does it usually require? I used to have a Vega GT, and it wouldn't even let you crank it unless your seatbelt's attached. So this would be kind of like logic, but what we understand is that every one of these signals usually are going to have a name. But for teaching class, what we do when we teach it, instead of us coming up with these names, is what we do is we just come over here and assign the inputs like ABC. So normally when we teach the class, we assign the inputs from A towards Z. Then we assign the outputs from Z toward A. Does that make sense? So the book is using X for the output. Now this gives us the ability to do a truth table, right? You understand? And what does a truth table do for us? Yeah, it shows how the output responds to all input possibilities, right? And I know I got 3 inputs, and we can calculate the number of entries on any base by taking the base and taking it to the number of bits. So we're using 3, so that means there are going to be 8 entries in our truth table. That makes sense? And then the way the truth table looks, we'd come over here and put the inputs on the left and then the output on the right. So it'd be the first input, and then basically if we do it like this, we can just start counting 1, 2, let's see, 0, 1, 2, 3, and I'm going to run out of space. Seven. 1, 2, 3, 4, 5, 6, 7, 8. And there's all my 8 inputs, right? So what would the output be for this first combination? It's an AND gate. All inputs have to be high, or all inputs have to be 1 to get a 1. So is all inputs high? Okay, so what would the output be? 0, right? Is all inputs high? 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 Yes. So that's what that means. All inputs are high. So in digital, when I use the term high, or I use it, that's in Boolean algebra, that's going to equal to a 1, right? You understand? And then if I say low, then that's going to be equal to what? A 0, a binary 0. So the truth table don't put highs and lows in there. It puts 1s and 0s. So this is a truth table for an AND gate. Now when we give the Boolean equation, the output always goes on the left, which is backwards from what we put there. But basically this is saying x is equal to A and B. Well, the problem is that we can't put x in there because x would be our output. So I said A is equal to A. What would you? That would be A output. Understand? So we can't use that sign. So we could use this, but later on that'll be confusing because AB might be the name of a signal and not the name of two signals, right? You understand? So we could use this. Or we could use the asterisk, which is very used to. In old days, this is the way, in old programming languages, this is the way you tell it. Not old, if you took anything like C, computer programming languages, this is the way you tell to multiply. Now, what we're doing in digital, this does not mean multiply. It's a symbol, right? You understand? What does it mean in digital? It means this is and by the way, when you do logic, you're supposed to use all uppercase letters, and that way it don't get us confused with the word and, right? Does that make sense? So anytime I do a logic operation like an OR, I'm gonna put the OR in uppercase letters. So in Boolean equation, it says, okay, your output is on the left because it's a math equation, right? And your answer, you know, you'd come up here and you'd say A is equal, if this was math, you might say, you know, Z is equal to M plus 2. Well, what you're solving for is always on the left. So in Boolean algebra, it's an algebra, and it's not algebra, it's a logic algebra. So a lot of the rules, some of the rules that you learned in math would apply to Boolean algebra, but they don't all apply. Like if we say x is equal to A and we can use the dot too, A and A. Now in algebra that would be A squared, but in Boolean algebra it's A. So we don't have any squares in Boolean algebra. I mean, you'll understand that. So some of the rules apply and some of the rules don't apply when we start coming back in. But one of the things that they teach you when you take your algebra class is how to take an equation and reduce it, right? Which means you make it smaller to solve for what you're solving for. What's nice about Boolean algebra, if you can reduce an equation, you're actually reducing the size of a circle. But in Boolean equations, the output always goes on the left, right? You understand that? So we'd say, we wouldn't say x is equal to A times B. We'd say in Boolean algebra or Boolean equations, we'd say x would equal to A and B. And all the things that you use to represent multiplication in algebra or in math, we could use the same in Boolean equations. Everybody understand that? Yes or no? This is the actual logic circuit for a standard TTL logic gate, but this is the actual symbol. So it looks like a D, backwards D, but we insinuate it, right? You understand that? Everybody okay? Yes or no? And of course, here's the truth table. This is the truth table for a 2-input AND gate. Everybody okay? And of course, what I told you is Is about as many inputs you'll see on one symbol, like this would be 4. And then what they do, if they have more symbols on this gate, what they'll do is they'll extend it, the input side out past the symbol, so they don't make the symbol bigger. You understand that? That makes sense? Inputs on the right, outputs on the left. An OR gate, the output at X will be high whenever A or input B is high, or both are high. And here's the Boolean equation. So in Boolean equations, we only got one option right there, and that is not plus. I don't want to hear anybody say that in this class, A plus B. That symbol right there we're using to represent a what? An OR. So the way we would say output X would equal to A or B. Now when we're talking about A or B, we're talking about them being a what? A 1. You understand that? Yes or no? Or it says A or B is a 1. That's what it's saying, right? Either one, yeah. Yeah, or high. Well, we got to get used to those terms. If I can say 1, or I can say a what? High. That makes sense. Or we can say a 0 would be the same as what we call a low. Now, what do we mean by a high? It means the voltage that we put on the input is going to be at a certain high level, right? You understand? And then when we say a low, it means the voltage that we're going to put on this would be at a certain low level. And there's a range. We're dealing with a logic called transistor logic. And why it's given that name is we're inputting on transistors and we're outputting on transistors. So the first letter says what the inputs are applied to, and the second letter says what outputs are applied to. And we'll learn a little bit about transistors in this class. We'll learn them to run them as digital switches, which is what we're going to do. Now we can't say, and what we do in digital, anytime you see the term DCC, this is going to be a plus 5 volt supply. Now in solid state, DCC can be any voltage level. But in digital, it's going to be 5 volts. And there's a 5 volts DC. And depending what we're going to deal with commercial logic, which means these are available. We have two versions. We have one that's made for the military and one that's made for us. The one that makes for us, there's a tolerance here. This is going to be plus or minus 5%. So it means this voltage could be anywhere from 5.25 volts all the way down to 4.75 volts, and it would still be okay. If it gets out of that range, then it means things are not guaranteed anymore, right? Does that make sense? Now, what TTL does is TTL, anything above 2.4 volts, this is a legal high. So this would be 2.4 volts up to 5.25 volts, right? And anything between 400 millivolts down to 0, this is considered to be a low. So what is it if it's between 400 millivolts and 200 and 2.4 volts? We don't know what it's going to be. The gate is going to accept it as something. It's either going to accept it as a high or it's not, or it's going to accept it as a low, depending on how accurate these things are. But we don't know. So that's what we're saying is we never want the input to be between that range. And this is between. This is supposed to be both. So this is considered to be illegal. That's my spelling illegal. Yeah, my brain would do it. ILLELEG. So anything between that range is considered to be illegal. And that's important to know too, because it's sitting down here at 2 volts, and you say, well, it's high, and the output is not responding, right? You understand? You replace the chip, and it does the same thing. So here, an OR gate, if any input is high, the output will be high. And then we have the abbreviation that we use, say any high equals high. So this is the symbol for an OR gate. We have this slanted input, and then this drops down like that. See that? So with any input, this guy's got to have a minimum of two inputs, a minimum of 2, right? You understand that? Could have more than 2, but it has to have a minimum of 2. Well, all we're going to do is use 2 because that only gives us four entries in our truth table, right? So is that any high? Huh? Is that any high? Is that any high? Is this any high? Is this any high? So that's the truth table for an OR gate. Some people want to see this as all, but if you look on an AND gate, you've got one unique output. You got one unique output, right? You understand that. On an OR gate, you're not going to have. Well, it's not true. We'll talk about that later on when we get into negative logic. But if we look, when we say any high, notice we've got 3 input combinations that gave us that high, right? You understand? So this is not an all. This is an any. Because it's not a unique combination, right? You understand what I'm saying? Yes, no. No, I consider this guy right here to be high. We got 2 inputs, A or B. So if I was to come over here, this is what we're talking about. I start off with that. So this is what I'm putting on the AB inputs. Is that any high? Okay, so what would the output be? Would be 0. Does that make sense now? Okay. And then I come over here and I put, which is what I have here. I have B as a 1. Oops, sorry. So I'm coming over here. I have B as a 1. I have A as a 0. So that would be that input right there. Is that any high? Okay, so the output would be what? So you're not looking at this. You're trying to vision this in your head, what's going on the inputs, right? Does that make sense? That make a little more sense? Because no, I don't consider that. I can't have plus 5 volts and 0 volts available at the same time, right? You understand that? We call that a short circuit, right? Not good. Are we okay? Any questions? And so the Boolean equation would be X is equal to A or B. Don't say plus in this class, right? And that's hard for you not to do. Why? Because you've been saying it all your life since the first time you did math in the first. What grade did we start mathing? First grade, I believe. It's been a long time since I've been in elementary school. So this is the actual circuit, and we don't need to understand this. We're going to talk a little bit about this just to understand what's going on the output over here. But and we'll trace this through. But notice we're inputting on transistors and we're outputting on transistors. So this is still what we call TTL logic. And VCC is plus 5 volts, plus minus 5%, right? Does that make sense? And here's the truth table for a 2-input OR gate. And of course, what we do is we start off with this. Then we'll bring in a maximum of 4 inputs. If we have to bring in more, then what they do is they do this. Make sense? They'll never go to infinity, but it'll go high. Technically, it could. What we're dealing with is standard packs. AND gates come in a 14-pin pack, dip, and we let y'all hold these, right? Yeah. And we'll look at what we call a pin out, which shows us how the gates, what inputs. What would be the maximum number of inputs I could have on an AND gate in a 14-pin dip? I could have 12 of them in there. How many inputs? No. Yeah, but what most people forget is for every gate we got to have an output. Every gate's got to have. We got to bring the output out somewhere, right? You understand? So we're going to lose 2. Yeah, we're going to lose 2. One for VCC on the AND gates that we're using, and one for common. So that leaves us 12 pins to work with, right? You understand? So what would be the maximum input a gate could have? Huh? Inputs? I say 11. That would be the maximum because you got 12 pins. One for the output, right? You understand? One for the output and then 11 left over for the input. That would be the biggest we could probably have. If I use 2 input AND gates, then we could have a maximum of 4, right? You understand? So it all varies on how. Y'all understand that? Well, if I use 2 input AND gates, then that gate only requires 3 pins. So that means I've got a whole wafer in there I can work with. So what I might do is I might come up here and put one of them right here. And what they do is they share the same VCC, but what I could do is I could come here and do what? I could put another one in here and let it use these 2 right here. Right, you understand? So each gate would require 3 pins. I got 12 to work with. So how many 2 input AND gates could I have in there? I could have 4 of them. Y'all understand? I got 14 pins to work with, guys. I've got power. What happens is we're going to draw this is each one of these gates could share the same power, just like your house, right? You got one panel box. The only thing they have in common is they're in the same package. So we could have up to 4 in there. If I went to 3 inputs, then it would require 4 pins, and I could have 3 of them in there, right? You understand? Up until the maximum of 11. That's the maximum we can have. So if I got, you could put inside a package. So it's kind of like, how many things can you have inside a box? Well, it depends on the size of what you're putting in there. So we're going to have at least 2 inputs, right? So the smallest, we'll have what we call a quad AND gate, quad 2 input AND gate. That's what they call them because there's 4 of them in there. Does that make sense? And the more inputs they take, the more circuit they require, and the less we can have in there. So it's just like I said, how much stuff can you put in a box? Well, it depends on the size of the thing you're putting in there, right? That makes sense? So we have what we call a pin out. Now, how's the pins numbered? Yeah, so we started on the left side, right? 1, 2, we look for the notch. 2, 3, 4, 5, 6, 7, then we 8, 9, 10, 11, 12, 13. And we call that the pin out. I don't know how the online book looks, but if you got the hardbound book, now we got the data sheets on all these gates. But if you buy the hardbound book, if you look inside the two covers, it gives you the pin out on a bunch of every IC that we will use. Now, pin out is what shows you what's assigned to each pin. Does that make sense? The next thing we'll look at, for some reason, the book jumps into timing diagrams. And what this is so this is an example of a timing diagram. So we got a 2 input AND gate, and what they're doing is they're putting a digital clock on one input. And then what they're doing is they're going to come up here, and we have this pin right here we call enable. So what's nice about AND gates and what's nice as OR gates is we can use one input as what we call an enable and a disable. Which means one input is going to decide whether the other inputs get through or the other don't get through. That makes sense? So what we're showing here is that if I put a 0 on this input right here, and we're putting a clock on this input right here, what are we going to get out? Can't say nothing. A nothing is a nothing. We're going to get a low out. That's the big difference. In digital, there's a big difference between a nothing. A nothing we call a float. A float means it's going to be some voltage, but it's going to be inside that illegal range there, and we call that a float. And that's what we consider to be a nothing. So what happens if I don't put this input right here to a 0? If I just leave a nothing there, then this gate is going to do something weird because I'm putting a illegal something out there, right? Does that make sense? So when we say we're going to be able to put a 0, or we're going to put a 1, or we're going to put a high or a low. Either one of those would work out in this class. But a nothing to digital is weird. We don't ever want a nothing. Okay. So that means I'm going to come over here and somehow I'm going to connect this thing to 0 volts. Not a nothing volts. It's going to be connected to 0 volts, right? You understand? So normally what we'll do is we'll come up here and we'll connect, somehow I'm going to connect that to circuit common, which is going to be, that's definitely going to be below 400 millivolts. So there's no way in the world I can get all highs, right? You understand? So what's the output going to be? It's going to be a low. And that's what they're showing us right here. This is this section right here. So this is what's on one input, right? You understand? So this section right here, we would say that this guy here is disabled. Does that make sense? Yes or no? When we mean disabled, we mean the output cannot allow the signal to pass. So what we done, and this is why these things became known as gates. Because what I'm doing is I'm opening the gate and I'm closing the gate, right? You understand? If I open the gate, then we're going to let the input get through to the output. If we close the gate, we're not going to let the input get through to the output. So if this input right here is a 0, I don't care how many inputs I have on this AND gate, right? You understand? So if I come over here and I have a 4 input AND gate, and I take this one right here, and I'm gonna come up here and I'm gonna put a pull-up resistor right here because I cannot put a nothing on here, right? You understand that? And I'm gonna put this to plus 5 volts. In fact, we don't have to do that. So right now with this switch open, what would I have on this input right here? If I have this switch open, there's a pull-up resistor, right? You understand? So that's, this guy right here basically draws no current at all. So for that resistor right there to drop any voltage, V is equal to I times R. So that V is equal to 0 times R. So what would my voltage drop be? 0 volts. If this guy drops 0 volts, if there's 5 volts right there, there's going to be plus 5 volts right there. Y'all understand that? Very, very, very important concept to understand in digital. So this is the way we have to use a switch. If I was to come up here and do that, then now I would have a nothing. Y'all understand that? In digital, we can't have a nothing, because if we have a nothing, that's a floating input. Okay? Yeah. Not even a low, it's a nothing. This is a nothing. So if I close the switch, I would get a low. If I open the switch, I would get a nothing. Okay? So if I come over here and put what we call a pull-up resistor right here, and then I connect this up to plus 5 volts. Now when the switch is open, I get plus 5 volts right there. When I close the switch, I get a 0. Y'all understand that? Huh? Well, I come up here and I do this resistor right here. Let's do it this way. And this is what I'm doing right here. So I've got a switch right here. And I'm taking my output right here. And I've got plus 5 volts right there. Now what would I get out right now? Guys, this is what you got to understand. For a resistor only drops a voltage if there is a current flow through it. So a voltage drop would be I get less out than what I put in, right? You understand? I have no current flow through the resistor. So the resistor is not dropping a voltage. If the resistor is not dropping a voltage, it means whatever I have here is going to be right there. Y'all understand? I have 0I. If I have 0I, and this is why, guys, this is exactly why I come over here and you learn this, and hopefully your instructor told you why. So let's say I have all these resistors right here. And I open that resistor right there. How many volts is this guy right here going to drop? 0. Why? Because there's no current flow in the circuit. So that means this now has moved right there. How much is this going to drop? 0. That means this right here has moved right there. How much is this going to drop? That means this right here has moved right there. This right here has moved right there. So what that means, if I measure across this resistor in an open series circuit, it measures the applied voltage. Why? Because nothing else in the circuit is dropping a voltage, because there's no watt in it. There's no current flow through it. So that's why hopefully you learn that in a series circuit, if you have an open in a series circuit, the entire voltage appears across that open. Why? Because nothing in the circuit is dropping a voltage. That's why I go over here and open this light switch over here. What would I measure across that light switch if I open it? The applied voltage. Why? Because these lights are not dropping a voltage, because there's no current flow through them. Right? How much would I measure across the switch if I close it? How much would I measure across a switch if it's closed? What? How much resistance does a switch have? Okay, it has none. V is equal to I times 0. So how much does a closed switch drop? 0 volts. So by George, guys, you're going to get yourself killed You go over there and measure across a closed switch and you measure 0 and you say, well, there's no voltage here. You reach up there and you're going to replace that switch, and what do? You get your butt zapped because a switch drops no voltage. Y'all understand that? That's the biggest mistake. I'll put that on the test. How much voltage should a fuse drop if it's good? All pretty close to 0. It's gonna drop a little bit because it's got a little bit of resistance. That's the way it blows. It blows because of I square R. But it's gonna measure really, really close to 0. Good job. Right. So this is why. So I come over here and I close this. This switch drops 0 volts. That comes over here and brings that and puts it there. That's why we got to have the resistor. So now the resistor's dropping all the voltage, right? Because I got common on one side and I've got high on the other. So I open the switch up, I get a high right here. I close the switch, I get a 0. And I never get a watt. I never get a nothing. So this is a real standard way to do push buttons in a digital circuit.
So when it goes back to saying that whenever you do have current flow through, you usually have to drop 710.
No, that's a diode.
That's diode.
Yeah. A diode is not a switch. A diode is a semiconductor. Semiconductors will always drop a voltage. That's a big difference. So even a transistor, I'm going to use transistors like a switch. A transistor will drop a voltage when it's turned wide open because it's not a switch, it's a watt. It's a semiconductor. If it was a switch, then it would drop 0 volts. So if I measure 0 volts across a transistor, it either means it's shorted, it's bad, or the power's not applied to the circuit. But a switch is different, right? Understand. So here we're using a switch, but you got to understand, in digital, we got to use switches, right? Somewhere. So like this whole keyboard right here, this is just hundreds of switches, right? You understand? And these switches have got to give me legal highs and they got to give me legal lows. Right? Does that make sense? So somewhere there's a pull-up resistor inside this keyboard. So when I close the switch, I get a 0. When I open the switch, I get a 1. Right? Does that make sense? Sort of. It's a little different the way the keyboard works. So what we're saying is that if I bring this input right here to a 0, then it don't make any difference. So if I came over here and close this switch, I should have left that. So I come over here and close this switch. What would the output of this AND gate be? It'd be a 0. That's exactly right. Well, what about those other inputs? They don't mean anything. I don't even care if they're highs. I don't even care if they're lows, right? You understand? As soon as you find a 0 on one input of an AND gate, then the output should be low, right? I don't care if it's got 100 inputs, which we won't see. We can fake it out. We'll show you how. But if I come over here and put a 1, if I come up here and open the switch, then what would the output be? Well, I have no idea. But now the other 3 inputs can respond. So what we've done is I've closed this. If I come up here and close this switch, I've closed the gate. I've closed the gate. Those other inputs don't make any difference. If I come over here and open this switch, then it acts like a 3-input AND gate. But I've added this 4th switch. I'm using it for an enable or a disable. So if I close it, I don't care what the other inputs are, right? You understand? If I open it, then it's going to respond to those other 3 inputs. So this is what they're trying to show us. Here they're using a 2-input AND gate, but we can use as many inputs as I want, right, or as available, and I can use one of them to either do what? Enable it or disable it. So right here, they're saying, if I put this 0 on this input, even though I'm putting a clock on that input, the output is going to be low. If I come over here and put a what? If I come over here and put a 1 on this input, then we allow this clock to go through. So now the output is responding to what's on this other input. So we can use AND gates as to enable or disable other signals. That makes sense? So this computer right here, everything in this computer is assigned a binary address. So we've got a group of pins coming out called the address bus, and it's a binary address. Oops, sorry. Is it erasing? No. What's happened to my eraser? Whatever. So let's say we have a device like this display, and this display is assigned just one address. And then what I do is I come over here and let's just use 3 bits. Oh. And we'll see later on. So I'm going to come over here and do this. And then I'm going to come down here and put my circuit. So we'll say this guy here has an address of 7. So I come over here and this is not going to work, guys. This will work, but it won't demonstrate the use of this pin right here. Oh, going to be another application. I can't think of one right now. So what we're trying to show here is how we can use one of the pins for an AND gate as a what? An enable or a disable. That makes sense? I tried to come up with an application, but I can't think of one right now in my head. If I did, we'll come back. Huh? So this is an OR gate. We'll look at this in a minute, but I could come over here and let's don't look at this right now. These slides got kind of out of sequence. Yeah, next door. Y'all meet next door. Y'all meet next door. So how many's that? Three so far. Huh? Yeah, y'all come in here half asleep. Y'all read these big old signs, or y'all forget what class y'all take. So let's do it this way. We'll try to, I'm going to use different colors. So here's the A input. So let's come over here and what I'll do is I'll draw it down here. Oops, sorry. What I need to do is move B down some. Okay guys, so what would X do for a 2-input AND gate? So this is a time and waveform that we should be looking at. Sort of, but what, yeah, I know what you're saying, but the expression is all highs equals a high. And that's the abbreviated. So all inputs have to be high before the output gets high. So what would I start off with? So this is a timing diagram that the book is talking about. Good. So I'd start off with a low. And it would go high, right? Then it would do what? It would go back low. Y'all with me? Keep going. Good. And I didn't finish this one out up here. I'm going to go ahead and do that. Oops. That's the wrong color because I couldn't get it. So everybody okay? Does that make sense?
But
Now,
I know one of them, they have either be mirrored or opposite. How does that work out? I think
no, when you say mirrored, you mean both highs or both lows, and that's not true on these guys. We'll learn it. We're going to look at a combinational logic later on called exclusive gates that do use mirror images of each other. But not these guys. Huh? No, the two diode gates we had next door. We had now I can understand. I didn't put a sign in there. So on diode gates, an AND gate is an AND gate, whether it's nothing but diodes or says all highs to get a high. Any in OR gate says any high to get a high, right? You understand that? So there's no mirror like you were saying a while ago. So mirror means if I had all highs or all lows, and that's not true for AND gates. These gates that we're dealing with now. Now later on, we have 5 basic gates. And what's the 5 basic gates, guys? ANDs, ORs, NOTs, NANDs, and ORs. And all digital logic are made from those 5 basic gates. So we'll get into later on what we call combinational logic, and that means they're going to utilize, somehow they're going to utilize these ANDs, these NOTs, these ANDs and ORs, NANDs and ORs to get more complex functions than what we're looking at here. But on these gates, we never have a true output when the input is are mirrored, right? Brian, you understand? So what they're saying here is that now let's do a time. Let's redo this and do it as an OR. Oops, didn't want to do that. And we'll do two inputs. More than inputs they get though. So this guy here says what? Any high equals high. So what would I start off with? Good. Nope. That little guy right there, right? Is that guy? And this is the OR with two inputs. Next door. Next door. Let's don't do 4 inputs. I just do complicated. So this guy here, we say it enables, if this is the enable input, next door. Your class is meeting next door. If we say this is enabled input, then what happens is that if the input is low, the output is disabled, right? You understand? If this enabled input is a high, then it's going to let the other two inputs work as an AND. Okay? Does that make sense? So what would happen is I'm using this as a what? Enable. So what we're saying is if I come over here and put this a 0 out there, this output's going to be a 0 no matter what those other two inputs ring. And we'll call this signal A and B. So if this is a 0, A and B means nothing. We got the gate closed. Right? Okay. If I come up here and make this a 1, then my output would work like a what? So if we come over here and I start this off now and I say A, B, and out here I put enable. Okay. So let's start off with this right here. Okay, so the output would be a 0. Let's go to this. The output would be a what? A 0. Right? I go to this. The output would be a 0. I'll go to this. Now the output would be a 1, right? Does that make sense? Then I go to this. Okay. And then we'll repeat this again. This will be a 0, right? This would be a 0. Oops. This would be a 0. And that would be a 0. Well, if the gate was enabled, then when I put that all on there, then that output right there should have been a 1. Should have been 1. So no matter when I put a 0 on my enable input, my output would always be a 0. If I put a 1 on my enable, then my 2 inputs, it acts like a 2 input AND gate with an enable, right? So what I'm doing is I'm using one input to either allow the other the other 2 inputs to work or not to work, right? Now an OR is exactly opposite. So if I come over here and take this enable input and I put a 1 on this thing, then what's the output going to be? It's going to be a 1. So what I've done is I've blocked the clock. The clock's not getting through, right? Now if I come over here and put a 0 in here, then whatever's on this other input is going to affect the output. So what we're doing is the clock is real easy to see. What I'm doing is I'm either letting the clock pass through or I'm blocking the clock, right? You understand? So an OR gate uses a low enable, an AND gate uses a high enable. So an OR gate, when you have it disabled, the output will always be a 1, right? An AND gate, if you have it disabled, the output will always be a 0. Okay, guys, y'all go ahead and take a break. And I want y'all all get up and move around. So this is a pin out of a 7408. And like I said, the textbook, I don't know about the online version of the book. The textbook basically gives you the pin out of a bunch of chips, integrated circuits. I guess I should have left it open. But if the online version doesn't give it to you. Then there's a, hopefully this one's up there. Data sheets. And this should have the data sheets. We're going to go over the data sheets in a lot more detail. No, we don't have 7408 up there, which is the one they're doing in the book. These are all the ones that we'll be dealing with during the semester. Let's look at a 7404, which is an inverter. So this is what we call a pin out. And what it does is it shows you how these different gates are wired inside the actual chip, inside the integrated circuit itself, inside the package. So a NOT gate. By the way, this is the only gate where it's different. The logic is called NOT. The circuit is called an inverter. So this is the only one where the name of the circuit, the name of the gate, and the name of the logic are different. So we'll come over here, it's hex, which means what? 6 of them in there, right? You understand? And they call it inverter, inverting gates. But the logic is called a NOT. This is the only one that's different. So an AND gate does AND logic. OR gate does OR logic. An inverter does not logic. So
Oh, say it again?
an inverter does not logic. So the name of the logic is not. Right? Does that make, but the name of the gate is an inverter. So this is the only one that's different. So a NAND gate does NAND logic. A NOR gate does NOR logic. An AND gate does AND logic. An OR gate does OR logic. An inverter does not logic. So that this gate, the name of the logic it does, and the name of the circuit is two different things. Now, why they did that, I don't know. I guess to make this class more confusing than it already is, right? So we have different methods we use to troubleshoot. So this is what they cover this thing here. We have a device called a logic probe. And we have two types. These are put out by B and K. Put out by R.
So between these two, what is the difference between these two?
What they're displayed by different things. We have two logics that we're gonna deal with this semester. One of them's called TTL, which is the one we're gonna deal with primarily. Y'all can. And then the other one is called CMOS. What CMOS represents as a high and low and what TTL represents as a high and low are different. Both of them use 0 volts as a low. So what do you think the red and the black is used for? It's used to power up the logic probe. So these guys don't have batteries in them. They power up off the circuit themselves. So these guys here run off of they run off +5. Well, they run off different voltages, but we're going to be dealing with TTL. So the first thing that we need to do is switch the thing over to TTL. So there should be a switch on here that switches you between TTL and CMOS, right? Y'all see it on there?
Yeah.
And this basically establishes what this thing sees as a 1 and a 0. So what we have is we have fixed power supplies on our trainer. So these are the ones we're going to use. So here's common. They call it ground, guys, but this is not ground. This is common. If it was ground, then I could take an ohm meter and put it on this one, and then I could go to this guy right here and it measures 0 ohms. This guy's not going to measure 0 ohms. So this is one of those situations where the person that did this don't know the difference between a common and a ground. Don't know the difference between a common and a ground. Yes or no? What's the difference between a common and a ground? You need to know the difference, even though people use it interchangeably all the time.
I guess the common you can send goes back and forth, and the ground can only go one direction.
No, that's not. Well, this is ground. This is ground on this guy. This is AC. So ground is somewhere there is a nice big copper rod driven into the earth, and this wire right here is connected. That is ground. Right? You understand? A common is just, so does my meter, does this guy here have a ground? No, it's got a common. So a common is just that reference conductor that everybody brings it back to the other side of the power supply. That's a common. So we have a common, right? You understand? And we have ground. Well, we have two different symbols. The symbol for a ground, where's my PowerPoint? The symbol for a ground, and y'all see me use it, the symbol for a ground is, we have two. We have this guy where they come in at an angle. This means chassis ground. And then we have this one. This means just ground, right? And then we have this symbol right here. This is common. So if it was ground, I could find that ground rod that is probably at our substation. I could take this guy right here. I would take this guy right here. This is ground. This is connected to earth ground. It should be if you don't cut it off, right? Or the plug's not wired right. This is not connected to earth ground. This goes to a transformer. So that means if I took an ohm meter and measured between here and here, it's not going to measure zero. It's going to measure infinity. So that means this guy right here cannot be ground, right? Yep, that makes sense. But that's one of the most misused terms in electricity. That big black wire on your car, that is not a ground, that's a common. Just about everybody calls it what? Ground. Y'all don't have a big old long wire running out of the back of your car to an earth ground somewhere, right? So this is our common. So that means what we need to do to power this thing up is, we have to hook this up to the plus 5 volt supply. Y'all can't see it. So here's plus 5 volts. And then this right here would be ground. And then we need to turn this to what? Right now we're going to turn it to TTL. This red light comes on when it sees a what? High. The green light comes on when it sees a low. And this light right here come on. It's not labeled. It comes on when it sees a pulse. I don't need to cram this thing. I don't want to. Okay. So right now, let's turn it on. Right now, this guy is seeing a what? High, low. Okay. So these are our digital logic switches right here. So this is where we're going to get just about all our logic right here. So when the switch is up, the guy gives me a what? High. And when the switch is down, it gives me low. These are going to be where we're going to use these to indicate. This guy right here is a clock, and this is the problem we have. So anytime you see that, it means it's doing this. So it can't be high. It can't have plus 5 volts and 0 at the same time. You understand that? So when you see both of them come on, what does that mean? It means you're seeing something pulse, right? You understand? If the red is brighter than the green, it means it's high more than it's low. If the green is brighter than the red, it means it's low more than it's high. If they're on about the same intensity, it means it's probably, it looks like this one is, yeah, it looks like it might be low more than it's high, but we don't really know. And that's why we have other test equipment that we can actually look and see what's going on. So these things are nice for troubleshooting real low, slow speed logic, which we're going to be doing a lot of here, right? And literally, guys, we don't even have to use one of these. We can use one of these guys up here. I need some jumper wire. don't have any law. I got to find mine. So we'll be using these a lot instead of a logic probe. So right now, this light emitting diode right here is off. You know, see that? So if it's off, it's probably seeing a what? Low. If it's on, it's seeing a high. That makes sense? Okay. So we'll be using this a lot more than we use a logic probe. Those are already available on the trainer. The only problem is that this doesn't tell us if it's legal or illegal. Let's see if I can make this guy work. So what's a legal high?
Legal high is 2.5.
2.4, close. 5.25, right? And then a legal low is
400 millivolts.
down to 0. So I'm putting a potentiometer on here. So a potentiometer gives us the ability to vary the voltage, right? So the problem with using the LED, if I can get this thing to reach up there. So right now I don't know exactly what I've got. The only way I can come up here and tell this is if I get a meter. Okay, where's all my meters at? They're next over. Let's see what our logic probe tells us. So this guy here is on. Both these are what? So this is the big difference. So right now, if I measure this, it would measure over 2.4 volts. Right now it's illegal. So if I put it in there and neither lights are on, it means that's illegal level. This guy right here is still lit up, right? The LED. So the problem with the LED, it's not going to tell you if it's legal or illegal, right? So this right here, so I'm still turning the pot. And now it's a legal low. Now it would be what? What we call invalid. That makes sense? Yeah. So your logic probe tells you whether it's a legal high or a legal low, right? You understand? Or it tells you if it's an invalid logic low. This LED don't tell you that. So the LED is going to come on. Oops, sorry. So the LED's on there. I don't know if y'all can see that, but this guy right here is still telling me it's invalid. So what's nice about a logic probe, it's going to tell you whether you got what, whether you got a legal high or a legal low or it's invalid. If it's invalid, you troubleshoot, right? You understand, right? Figure out why it's not at least 2.4 volts or it's not below 14. Of course, I've got a potentiometer hooked up, and that's what we use a potentiometer for. So what we're going to do, one of the labs we're going to do is we're going to take a logic probe, we're going to get a pot as soon as I can find where our potentiometers are at. And we'll see exactly what voltage level this thing here sees as a 1 and what voltage level it sees as a 0. That's one of the first labs we'll do. And then we're going to come up and figure out this trainer, all these switches and what they do. So these are the main things we're going to be using here. We're going to be using the plus 5 volt supply, right? And then we're going to be using these to input it. So we got 8 switches right here, which gives us 256 combinations. We're going to start out with using 2 input gates, and then we'll probably be using the LEDs to see what's going on the output with the inputs, right? Does that make sense? So logic probe. So the first thing you're going to have to do to the logic probe is do what? You have to select the logic you're looking at, and then what are you going to do? You're going to hook it up to the plus 5 and then the common, and then it powers up off the circuit. So logic probes power up off the circuit. The problem we have with logic probes is they don't do much for us on high fast moving signals. So on fast moving signals, we either don't see anything or we have this guy right here. We got here that says what? Can y'all see what mine's not focusing in? Memory. Memory has got a latching circuit in there. So if it's setting at a constant 0, and then if it's setting at a constant 0, and then all of a sudden the red light comes on, what it'll do, it'll latch that for you. So what we can do is we can see how moving. We can see if one pulse occurred, but if we're getting multiple pulses, then this guy right here won't do much good. Are you okay? Questions? Pretty easy to use. The other one we have available is an oscilloscope, and we're going to be using that a lot this semester. So what you probably need to do is, if you're not, we have what we call a pulsar probe. A pulsar probe generates pulses for us, and it's an aid in troubleshooting. So we can use this guy to generate a signal and try to anticipate. I didn't give out the pulsar probe, but we have those too. The next line of defense we have is what we call a oscilloscope. What's nice about an oscilloscope is that it shows you technically, it shows you what is there. It don't average things out. It don't blink lights. It shows you exactly what's there. So this guy here's got its own power supply. So this is an oscilloscope. And I got a plug somewhere. Have y'all ever done that? Plug the plug into it. Oh, y'all going to be using a little cheaper probes, but we have, this is the reference. This is ground, by the way. Once we hook this up, then our craner is connected to that. And then this guy right here, we have different tips we can put on this thing. And then what I'm going to do is I'm going to take this. Now, this right here pulls off, guys, but you got to be real careful. As soon as you pull that off, this and this are referenced together. That means if you accidentally touch this metal up against something, you've created a short circuit. So we have a little cap. I need to find them that we can put on this, but if you got one at home, you could put a piece of tape around it when you pull this off, because this makes a really, really nice probe right here. It's nice and sharp. So what I'm going to do is I'm going to put this up into my switches. So what we're going to do is I'm going to set my scope. So this is where we can set the position. We have 2 channels on this, and that's another limitation for us as far as troubleshooting goes. Some of our logic gates might have, 8 inputs and 1 output. These guys right here, it's going to be hard to see all highs to get a high, especially when they're changing, right? I understand that. This guy we can look at 2 channels at once. So we have channel 2, which is the blue line, and channel 1, which is the yellow line. I'm going to put it on channel 1. I'm going to put it on 1 volt per division. This shows a 1. Y'all can't see it over here. It's not focusing in real well. This shows me my 0 volt reference. So what I can do is I can put the 0 volt reference anywhere I want to. Normally what we do on digital is we put it on 5 volts per division. I'm sorry, 1 volt per division. So it means if it goes up 5 divisions, that means it's 5 volts, right? So I'm going to put this on my switch. And what's going on with scope? This late plan for oops. So let's walk. I'll turn off channel 1. Channel 1 probe is missing. So this is 1 volt per division. So we can use this as a logic probe, right? You understand? So that's 1 volt per division. Then basically that would be 1 volt. If this is 1 volt, and each one of these is 0.2. So I know to get a legal 0, I'd have to be right there. And this right here would be 2 volts. In fact, we'll show you how to set it where you can see it real easy whether it's a legal high or legal low. Now what's nice about a scope is that we have the ability to actually see what's there. Now the problem is my scope's taking pictures and it's not synchronized with the signal that I measure. So what we do is we have what we call a trigger over here. So I'm going to hit the trigger button. Right now it's set to trigger on channel 1. Well, I'm not using channel 1, so I need to change that over to what? Channel 2. And then what we need to do is we need to set what we call a trigger level. So if y'all can see the white line moving through there. Well, no, we just set it inside the waveform somewhere. It can be anywhere. It's just when I get it out of the waveform, now it's not synchronized anymore, right? You understand? All you got to do is just get this guy down inside the waveform itself. And then what's happening is our scope's going too fast. So this is called how fast the scope is going right here. So what we can do now is what we can do with the oscilloscope is we can see actually what's there. All the logic probe would do is the green light and the red light would be coming on. So my logic probe, I can see I can change the duty cycle with this guy. I can change it to that. So the logic probe, the oscilloscope shows me what's there, but the problem with the oscilloscope is I can only look at two inputs. I can only look at two things at the same time. So if I've got a 2-input AND gate, I might could look at both inputs, but then I don't know what's going on with the output, right? You understand? If I look at one input and I reference that to the output, it doesn't do that much good. So what does that mean? Well, that means we got another piece of test equipment. And we called it a logic analyzer. This is our logic analyzer. You can look at up to 32 things at the same time. So these are the actual probes. And I need to go out and find what's happening to these guys. So we got 2 of them. Each one of them's got, you can look at 16 things at the same time. So what we could do is if we put 16 traces up there, and we could actually look at what's going on with 16 inputs. This guy's very expensive. The logic probe is your cheapest alternative, but the problem with the logic probe is what? One thing at a time. So that's one thing. So there's no way in the world I could look at. It works real good with static symbols. Signals, things that don't change. Right? You understand? It doesn't work well with things that move real fast. It don't respond fast. That makes sense? The problem with the oscilloscope, which moves way up the ladder as far as price goes, these logic probes, you could probably get these for less than $20. In fact, there's diagrams out there where you can make your own logic probe. Oscilloscope, an analog oscilloscope is on the order that would measure. This is a 25 megahertz oscilloscope, which means it can measure a signal moving up to 25 megahertz. It doesn't mean it's not going to measure it. It's just it won't be accurate above that. This guy right here can operate at I think this is 100 megahertz. This is 100 megahertz. We can use this as an oscilloscope, but we also can use it as a logic probe. As a logic analyzer too. That guy's big dollars. Big dollars. But if you did a lot of troubleshooting on these things, then you might could justify those. Okay, so the first low active output we're going to look at is something called a inverter, which does not logic. Used to complement or invert a digital signal. So in logic, the term complement means opposite of. It's not that we're saying, you look good today. So in logic or digital, it means it's the opposite of. This would be figure 3-20, should be 327 in your textbook. I don't look like anybody's got their textbook. So, well, I can't tell you. Yeah, I have to say I have no idea how to tell you. This is something new. So as soon as you figure out, Brian, you need to let me know because I have no idea. This is something brand new for us. And so this is the symbol of an inverter. Now what we've done, and this is where it gets a little confusing in math. So normally what people want to do is they come up here and they would want to do this. So this means low active. And we put a bar above it. So normally what people want to put is this. That would be like in algebra saying a minus A is equal to B. That's illegal in algebra. Or B plus C. You have no, so when you solve for algebra, what you're solving for will always be positive, right? Understand? That makes sense. So the expression we would say a high end gets us a low out, but we could also say a low end gets us a high out. When we do the Boolean equation, anytime we say this, then we're going to say x is equal to not a. So this says since it don't have the input, this is said if the input is high, the output will be what? That bar means it's what? Low active, right? But what most people want to do, so this, since this is X and this is Y, this is X and this is A, what's the common mistake people will do? Since that's got that bubble right there, so that bubble right there means, this means it's low active. So what they want to do is, first of all, they want it, since on the symbol, the input is on the left and the output is on the right, what do they want to do on their Boolean equation? They want to put the inputs on the left and the outputs on the right. The next thing they want to do is, since X has got the bubble, they want to do that. But that would be the same in math as trying to do that, right? Yes or no? So in math, we never solve for a negative number. Our answer might be negative, but when you put the A, it doesn't have a minus sign. It always is understood to be positive, right?
So the dash line above the X is equal to the A is equal to the line above the A. So they say the same thing.
It is. You're right. It's saying the same thing. Here it's saying if the input's low, the output's going to be high. That's what it's saying. But when we talk about this, we say a high input gives us a low output. So that's where it kind of gets kind of confusing. But you got to understand, if a high input gives us a low output, then a low input will give us a high output, right? Or vice versa.
And the line in front of the A equals B, B and C.
No, what I was saying up here at the top, there's no B and C. All we got is A, and then we got an X. What I was saying is that mathematically, if I was to put a minus A is equal to B plus C, then that's not mathematically correct. If you were doing algebra, they would do what? I don't know if they, I guess I don't know. Yeah. So what we're saying is what we would do mathematically. Now we're not going to do this in Boolean algebra. It's a little different. But what I would do is I would come over here and change the sign of this one, and then I would come over here and make both these negative, right? You understand? Well, actually you'd do this. You'd put that and you'd put a minus sign over there, and then this right here would become what? Positive, and that's what you would do in algebra. So what we're saying is that the output, okay, the output over here is always going to be, it's not going to have a bar above it. Right? Makes sense? So a NOT gate, we use this all the time. Now, I don't want you to learn it like this, but think about this. Let's say we take an AND gate. Well, here the truth table would be real easy. So here we'd have, so this output is X, input is A. So I'd have A, and then I'd have X. I'm only going to have 2 entries in my truth table, right? You understand? Because I only got 1 input. So I'd start off 0, right? What would the output be? 1. And then 1 would give me a what? 0. So that's the truth table for a inverter, which does not logic, right? Now let's say I take this inverter and put it on the output of an AND. And there's X right there. So if I was to come over here and so we got 2 inputs, so that would give us 4 in our truth table, right? So a 0, 0 would give me a 0 right there. And then we're going to invert it and get a what? 1. And then I put a 0, 1. This is still going to give me a 0 right there because I'm looking for all highs, right? You understand? The output would still be 1. I put a 1, 0, the output would be 1. I put a 1, 1. That's going to cause this to go to a 1, which is going to cause the output to go to a 0. So when I combine that inverter with an AND gate, we get just the opposite of what we got with an AND gate. And this is the truth table for what we call a NAND. Now, we don't do this. What we do is we come up here and the symbol for a NAND, we put the bubble right there. Yeah, we don't do this. This is a NAND gate. You buy these things. What does this guy say? It says all highs to get a low. So what we do is we look at the bubble. Anytime I see the bubble, I'm going to say what? Low. If I don't see the bubble, I'm going to say what? High. Yeah, but it's not. It's a NAND. A NAND has the bubble.
That's what I'm saying. So with a NAND, you will always have both.
Always.
So it means it'll always be low.
No, it means all highs will give me a low. That low does not mean always. It's just like this bubble right here does not mean it's always going to give me a low, right? You understand? So we did the truth table. We did the truth table for this guy right here. So what's the truth table for this? So we said the truth table was A, B, I'm sorry. First of all, you need to know if an output of a logic gate is always a low, I wouldn't put a gate in there. I would just connect to the common. If the output of a logic gate was always high, then I wouldn't put a logic gate in there and waste my money. I would just connect it up to power. So these outputs are not always going to be high, and they're not always going to be low. They're going to respond to a certain logic, right? So an inverter, if the input is low, the output's going to be high. If the input is high, the output is low. So this is telling us what's going on between the input and the output. So what this is telling us, if I don't have it there, we do have another, this is not a logic gate, this is called a buffer. That guy does no logic, so it's not considered to be a 5 of the basic gate. That says, if the input is high, the output would be high. This guy is telling me, well, if the input is high, because it don't have a bubble, this is telling me the output will be what? Low. This is telling me if all the inputs are high, the output will be low. Okay. So if any input is low, the output will be high, which is weird. So the truth table, that's what it's saying. The line over, a bubble means it's what? If we see a bubble on a symbol, it means it's low. Low active. Not low, it means it's low active. It's true when it's low. So that means and that's relative to the input. So what's the input saying? High. Right? You understand? Why? Because there's no bubble. What's the input saying? What's the output saying? Low. So it's saying when the input is high, when the input is true, the output will be true. So the input is true when it's high, which means the output's going to be true when it's what? When it's low. So a high in will give me a low out. So what will a low? So if I put a low on the input is false, so the output will be false. So if the input is low, the output will be high. So the bubble does not mean it's low all the time. Just like the not having the bubble doesn't mean it's high all the time. It shows you what it's looking for, right? You understand? So that means for this output right here to be true, the input has to be true. Well, if I come over here and of course in Boolean equation, let's not look at that. Boolean equations will use the bar to indicate low active, right? So what we're saying is I come over here and see this expression. Well, let's look at an and. I don't see the symbol for an and. So this is a symbol for an and. So as soon as I see that symbol, I'm going to start off with all. And when we talk about the first all, we're talking about these two right here. It doesn't have a bubble, right? Y'all understand that? So I'm going to come over here and I'm going to say all. I don't have the bubble. I'm going to say all what? Highs. Right? Equals. Then I look at that right there. It's got a bubble. I'm going to say equal to what? A low. Because it's low active. It's true when it's low. So when the inputs are true, the output will be true. So here it takes all highs, all inputs have to be true on the NAND gate, right? You understand? To get the output to go true. So if I came over here and drew it like this is going to say all highs to get a high. A NAND gate says all highs on the inputs to get the output to go low. So if I drew the truth table for this gate, are all the inputs true? It's an AND gate. Is all the okay? So the output's not going to be true. Are all the inputs true? No. So the output's not going to be true. Are all the inputs true? No. So the output's going to be true. Not going to be true. Is all the inputs true? So the output's going to be true, right? You understand? Now let's look over here. Are all the inputs true? No, so the output's not going to be true. Because it's true when it's what? When it's low, right? You understand? Are all the inputs true? No, so the output's not going to be true. Are all the inputs true? No, so the output's not going to be true. Is all the inputs true? Yes, so the output will be true. So an AND gate says all highs to get a high. A NAND gate says all highs to get a low. So what's a NOR gate going to say? Any high to get a low. So it's going to have a bubble on the output.
I guess I kind of get what it just said. It's just basically the opposite of AND.
The output's opposite, yeah. Because the AND has a high active output and the NAND has a low active output. So that means anytime we see an AND symbol, this thing that looks like a D, anytime we see the thing that looks like a D, we're going to say all. And what we're talking about is the active state of the inputs. What's the inputs looking for to be true? So if I don't see any bubbles over here on the input, and I could make up a signal, guys. I could come up here and do this. And what would that guy say? That guy would say all lows to get a low, right? You understand? I mean, we're going to run into these. So what you're looking at is anytime I see that D symbol, I'm going to say what? All. Sorry. Yeah, later on we're going to learn those symbols. First of all, we're going to learn these guys right here, and then now we can understand those. So what I'm doing is I'm looking at bubbles. If I don't have bubbles, then they're true when they're what? When they're high. If they do have the bubble, then they're true when they're low. So here we look at this symbol. We're going to start off all, right? You understand? And we'll say what? All highs to get a what? To get a high. I'll look at this one, I'm going to say what? All highs to get a low. And then later on, we're going to get into some weird ones. Well, they're not weird. No, we can't do an AND or an OR. I don't know where this came from because we only got one input. We can do an inverter, right? So what would the inverter look like? What would the output of the inverter look like? So let's start off what? Start with A. Yeah, that's exactly right. It's just going to be what? Opposite of the input.
I think really, everything about really seeing something like this in the first slide. Just to give an example of everything that's going to go through and say, I think this is what we're talking about.
I can't either. I mean, I don't remember. Now this would be the mirror. This would be the mirror this would be the mirror image of the input because mirror is opposite of, right? But it just came up for the not for not logic and not for any of the rest of them. A NAND gate, we're okay there. So what do we say about a NAND gate? Okay. Now this is where it gets kind of confusing. So I come over here. Well, it's not really confusing. Not for me anyway.
Yeah.
Now this is where people gets into problems at A, B, and X. So when we do a Boolean equation, we do X, right? Okay. And then we know this is AND logic. So A and B. That's better to use than the asterisk, right? Okay. Now what are we gonna do about the bubble? I can't put bar over there. Why? It's on the we can't the term on the left hand side of the equation can't be negative. It's always got to be positive. So you learn in algebra how to swap those signs. So what we do on the Boolean equation is we move that x, that bar, from here, and we put it right there, all the way across the whole thing. So this is the Boolean equation for a NAND. So basically, this is telling you just to take this and then invert your answer. Let's see what I did up there. Oh, That's that NAND. X equal A and B, B, if we keep having the input C and D, then what we'd do is we'd put a bar above the whole thing. And that means the output is low active.
Or is it and is
asterisk or the dots. Anything you use, and like I said, we could put AB, we could put ABC, right? You understand? Now, technically, that would be okay, but later on, when you get into true schematics, these signals are not going to be called ABC. They're going to be given a name depending on what they do. That makes sense? The textbook, and I hope I scanned these guys. If I don't, I'll have to find it. So the textbook, and I don't know how they'll do this on the soft version, but the textbook has got two schematics in it of an actual digital circuit. I thought I scanned those things. This is the schematic on our train. So this is the power supply. So this is the symbol of a transformer. This is a symbol of a rectifier that turns AC and DC. These are filter insert devices. And then this is a regulator right here. So this is a 12 volt regulator. And then that would be this little knob sticking up here that says plus 12 volts. Here's minus 12 volts. This is the 5 volt regulator right here. You can actually see this on the side of the trainer because it's a high current regulator. This is the schematic of our digital trainer. We'll look at this. No, that's not all of it. Now, so this is those switches up there. You can see there's that pull-up resistor we're looking at. So if I flip this over, then it's going to give this a high. If I flip it over the other way, this goes over to what? Yeah, ground. You can't see the ground symbol. These are the little circuits that's running the LEDs for us. And you'll be able to read this before the end of the term. This right here is the function generator. This is what's generating these clocks that will be used during the term. We won't get into that. But I don't see the schematic that's inside the trainer. Dang it. So anybody that buys the book, the hard book, you buy that and let me scan those things out because I wanted to show you the actual way that the circuits, each signal given a name. And if it's given a name, like Brian, then I can't put B, A, so they'll be given, the signals will be given names depending on what they do. Or they try to give you names on what they do. So even though this right here would be, even though that would be legal in this class, it wouldn't be, y'all understand what I'm saying? So if I came over here and did this, and you had 3 inputs, call this one A, B, C, and then the output X, then this works a lot better when you plug it in. So we could go X is equal to A, B, C, and that would be perfectly legal, right? Y'all understand? But if this signal right here was called AM, and this signal right here was called BD, and this signal right here was named CK, then if I come up here and put X is equal to AM, CD, CK, you would think that would be a gate that had 1, 2, 3, 4, 5, 6 inputs on it. So the more correct way would be A is equal to A and B and C, right? So that way you know their individual inputs. Down here, X is equal to AM, then I put AND, then I put CD, and then I put AND, and then I put CK. Now that makes sense. Or you could do it like this. You could put X is equal to AM, CD, CK. So all these symbols are legal for multiplication. We just don't use an X. So in math, an X is legal for multiplication, but in Boolean algebra, an X is not equal for an AND, because an X is going to be assigned to one of the pins, right? Does that make sense? So all these other symbols, the dot between the inputs, the parentheses between the inputs are legal. And this will be legal, okay, in this class, but you won't use that. So there's that, oh, and then the NOR. So here's an OR, same as the OR, except that its output is what? Low active. So when we see this guy, we're going to say what? So if I see this symbol, I'm going to start off with any, right? Any high will equal a what? Low. Good. So this truth table, if I call the output X, A, B, X, it's going to be the opposite of an OR. So is that any high? No, so the output will be high. Is this any high? Yes, so the output would be low. Is this any high? Yes, so the output would be low. Is that any high? So the output would be low. So it's the opposite of the truth table of an OR. And that's our 5 basic gates. What's our 5 basic gates, guys? And, or, nor. Yeah, don't forget the not. So this is a what? Don't look at the, so this is a and, or, nor, nan, Rich, nor, and this is a man. The only symbol they don't have up here is a not. Okay, guys, take a break. Kept y'all over, I'm sorry. 2 minutes, and then we'll come back and we'll talk about lab. And I don't know about Wednesday. Everybody's got Cougar Alert on your phones, right?
Right.
Because we're supposed to snow tonight, into tomorrow, but they're not really sure what's gonna happen between how, is the snow gonna melt before Wednesday night? Cause Wednesday night's supposed to be really, really cold.
We're looking right now, it's too warm.
Yeah, but it's gonna crash. It's supposed to get up to almost 60 today. So I need to get up and move around. So what was I on? Well, y'all don't need to close the door over there. That's for the police and the, so this door over here will not latch unless you pull it.